Good day, everybody, and once again we meet to discuss that physical science. We've been busy with the November 2020 paper from DBE. All right, so if you haven't subscribed, please just make sure that you're part of the family. And for those of you who may need assistance with mathematics or physical science, please, we can be your plug, right? As we have been. Our email address is info@mlungisinkosi.co.za. All right. So we're looking at question 10 on the photoelectric effect. Okay, so and I hope that you'll be able to understand and follow on. For those of you who might still find this section challenging, please, we've produced a very, very lovely video on it. Okay, just check under videos. All right, you'll see the one that is on the photoelectric effect. I tell you, if you are experiencing problems, you will be cured in just about 30 minutes or so. All right, so let's start with this question. Okay, they say an experiment is conducted to investigate the relationship between the frequency of light, okay, incident on a metal, and the maximum kinetic energy of the emitted electrons from the surface of the metal. They say this experiment is conducted with 3 different metals. Now, you can already see from that graph there that you were given 3 different metals. And please remember, each metal has its own work function. Okay? When you look at that graph there, if we're considering that as their frequency, that would be our threshold frequency there, right? So it means that the threshold frequency for, potassium is much less, okay, or it means it has a lesser work function than in this case zinc. So you would find that it actually you require more energy to emit electrons in zinc than you do in potassium. Okay, right. Okay, let's not talk too much. All right, so let's get right into the questions. They say to us, name the phenomenon on which this experiment is based. Okay, and of course that phenomenon is the photoelectric effect. Okay, they say name the physical quantity represented by X on the graph. I want to kind of show you where this comes from. I don't know if it will be of value to you, but I mean, it would be somewhat important. So we know that usually when we deal with this section, we're going to have E, which is the energy of the photon. It's equal to the work function plus EK max, okay, the maximum kinetic energy of an electron, right? But now remember, on the y-axis, now you've got EK max. So let's make EK max as the subject of the formula. So EK max would be equal to E, right? And obviously minus the work function. Now in this case, where do we get the frequency, right? This would be HF. So we know E is equals to HF minus omega 0. So if you think of this as a straight line function where y is equal to mx plus c, right? Now it means our EK max is our y, our gradient is our Planck's constant, our x is f, and it means that our c here, which would be normally in a straight line function, this would be your y-intercept, right? I don't know why I'm forgetting y-intercept. So this would be your y-intercept. So it means that if you look at this equation here, if you're looking at this graph here as a straight line, your y-intercept is that value at x. And in this case, what does our y-intercept actually show us? That would be the work function. Okay, right. So I thought perhaps it might be of value just to show you where this comes from, as opposed to just telling you. Okay, so let's go on to the next question. They say, which one of the 3 metals needs incident light with the largest wavelength for the emission of electrons? Now remember, the largest wavelength, okay, the largest wavelength, okay, I'm going to just take this equation for frequency and wavelength. In order for, okay, let's rearrange it. Wavelength is C over the frequency. In order for wavelength to be largest, okay, it means frequency should be the smallest, okay? So essentially what they are asking us here is which of the incident light, which one of the three metals rather needs incident light with the smallest frequency, okay? Do you see? So if you think about it, which one needs incident light with the smallest frequency? That should be potassium, right? So our answer there should be potassium for 10.3. So 10.3, that should be potassium. Okay. Right. They said give a reason for your answer. Of course, as we've just explained, that the higher the smaller the frequency, right, the longer the wavelength. And in this case, they said the one with the longest wavelength. And in this case, we realized the longest wavelength would mean, the smallest frequency. And in that case, the smallest frequency, you can already see that's frequency against time. The smallest frequency is that of potassium. Okay. Right, so they say define the term work function in words. Okay, we say this is the minimum energy required to emit electrons from a metal surface, right? So it's the minimum energy required to emit electrons from a metal surface. Right, let's go on. I'm just going to continue to the other side. They say calculate the work function of platinum. So let's do that. So 10. Let's calculate that there. So that's 10.5.1. Okay, so we're looking for the work function of platinum. Now, to get that work function, okay, I am simply going to find the frequency of platinum, the threshold frequency. Remember that where it starts, where it cuts the frequency axis, that's our threshold frequency. So this is going to be HF0. Okay, so Planck's constant, remember you're given as 6.63 times 10 minus 34. Remember this is given to you, multiplied by the frequency. Okay, I'm just going to move this a little bit. Okay, multiplied by the frequency, and it looks like we've got 1.5 there. So that would be 1.25. So this would be 1.75. So that looks like 1.75 times 10 to the power 15. Okay, so that's 1.75 times 10 to the power 15. Okay, and what is our frequency value, our work function rather? Right, I get a value of 1.16 times 10 to the power minus 18 joules. So that's the work function of platinum. Okay, so there is its value there. Right, and then the last question, they say calculate the frequency, okay, of the incident light that will emit electrons from the surface of platinum with a maximum velocity of 5.6 times 10 to the power 5 meters per second. Now, we want the frequency of the incident light. So let's take our equation, our formula. We know energy would be equal to the work function plus EK max. Okay, so now we want the frequency of that light. So we'll say H multiplied by F. Okay, as I said, if you haven't watched the full video on this, please make sure that you plug yourself there. Okay, you'll find it under videos, and it will really help you quite a lot. So this would be 1.16. Remember the work function we've already calculated, times 10 to the power minus 18 plus. Now remember, they'd given us speed there of electrons. So how do we then calculate the kinetic energy? We know this is going to be half of the mass multiplied by velocity squared. But remember what is moving? We're talking about electrons moving. And what is the mass of an electron? I want to just show you where you get that value there. Okay, in your table of constants, they always give you the mass of an electron, and there it is there. Okay, it's that ME value. That's 9.11 times 10 minus 31. So we can use that one there. 9.11 times 10 to the power minus 31. And the speed, okay, I'm just going to move this a bit. So the speed is 5.6 times 10 to the power 5. But remember to square that, okay? And let's just try and find the frequency. So remember, to get the frequency, you'd need to divide by Planck's constant again. So I'm going to take everything here and divide by Planck's constant, which is 6.63 times 10 to the power minus 34. Okay, right. And of course, you can knock yourself out and find that answer there. And you know, if I work it out, okay, I get a frequency value of 1.96, or you can say 1.97. Okay, you can say 1.97 times 10 to the power 15 hertz, and that would be the frequency that you would require to emit electrons so that they move at that speed that is stipulated there. Okay, right, and that is essentially how we answer this section. All right, and please just make sure that you know, you tell your friends and your family members, you know, anyone that's in matric. Okay, just tell them that of course we're learning quite a bit here. And yeah, for those of you who haven't subscribed, please just continue to you know, go ahead just immediately after you watch this, go and hit that subscribe button so that we can make sure that our numbers are growing. And thank you so much, ladies and gents, and I will leave it here. Hope you enjoyed this paper. Sharp, sharp.